Hi everyone, welcome back to chemistry. In this video, we're jumping back to chapter 2 to talk about section 2.2, measured numbers and significant figures. In the previous video, we jumped over to 3.3 to talk about temperature conversions. So if you haven't watched that, go ahead and go back and watch that first and then come back here. Okay, so 2.2, measured numbers and significant figures. So anytime we make measurements in chemistry or science in general, there's always going to be some degree of error or uncertainty in those measurements. And we want to make sure that, because we're human, and we want to make sure that other scientists know that there is a degree of error in the numbers that we're reporting when we're measuring things. And the reason that there's always some error when you're taking measurements is because you're always measuring something and making an estimate about where the final digit in that measurement is located. So let me tell you what I mean by that. So looking at this piece of wood and this ruler right here, if you're trying to measure the length of this piece of wood, you're looking at it and you're thinking, okay, well, it definitely is past 4 centimeters, right? It's also not at 5 for sure. It's really not there yet. And then, with our eye, we can kind of see, well, it looks like it's about halfway through at 4.5 centimeters. Actually, let me write that 4.5 over here because I have more stuff I want to show you. So 4.5 centimeters. But we're not really actually certain about this number. I mean, looking at it with our eye, we can say we think it's halfway, right? But we don't have any actual tick mark right here that says 4.5 or that indicates that it's 4.5, that it's halfway between 4 and 5. So we're actually estimating this last digit right here. Sorry, this last digit. Okay, and that checks out because the last digit in your measurement is always an estimate. I'm estimating that this piece of wood is about 4.5 centimeters, but I don't know for sure. If there was a tick mark here, I could say with more certainty that it was at 4.5. But because there isn't, I have to estimate that last digit. I'm not estimating this digit. Why is that? Yeah, because I know it gets past 4, right? I just don't know how far past 4 it gets. So today the goal is to be able to identify if a number is measured or exact. Exact numbers would be numbers that you don't actually have any degree of estimation to them. They're exact, they're known. Measured values is things like this, where you're measuring something. It could be the length, it could be the mass. We take all kinds of measurements in our daily lives and in chemistry. But there's always a degree of error in those. And then we also want to determine the number of significant figures in a measured number. And we'll talk about what that means in a little bit. That's probably some new vocabulary, and that's okay. So measured numbers. Measured numbers are numbers obtained when you measure any quantity. So height, weight, temperature, length. Anytime you're taking a measurement, you're going to end up with a measured number. So to write a measured number, you're going to first observe the values of the marked lines. So for instance, that was when I said, hey, it's at least 4, but doesn't make it to 5. So we did that. And then our second step is to estimate the value of the number that's between the marks. So where does this fall? Well, I think 4.5, an estimation. So we did that as well. The estimated number is always the final number in your measured number. Again, sorry, I hope I'm not making you dizzy. 4.5, this would be the estimated value. The final number in your measured number. Okay, so let's take a look at this. We did this first one here, so A is done. That was the example we went over before. Now let's look at B. So B, we are thinking the length of the object is 4.55 centimeters. Notice we get an extra digit here, okay? And the reason that we have that extra digit is because now this ruler has more tick marks. More tick marks means that we can make more accurate estimations, because if we have a tick mark here at 4.5, 4.5, we know that the ruler at least makes it to 4.5, but does not make it to 5. So we're certain of that number there now, but we're estimating this number. Okay, so we know it makes it to 4.5. The next tick mark is 4.6. It doesn't quite make it there, right? And I apologize, I'm really bad at drawing straight lines, but you get the idea. It doesn't quite make it there. Where does it make it to? Where do you think that would be? Well, I think I agree with the book. I think it's about 4.55. So because it falls between 4.5 and 4.6, looks like it's about halfway between, so I think it's 4.55. But I could be wrong, right? It could be 4.56, it could be 4.57. I don't really have any way of knowing for certain what that last digit is. Oh, shoot, sorry. So, get back to my thicker pen here. So this number here is your estimated digit. Okay, I hope that makes sense. As always, if you have any questions, come see me during office hours. All right, and then for the last one, we see that it falls pretty much exactly on 3 centimeters. Okay, so we're going to report 3 centimeters. And then in this case, we do want to show that there's that it falls exactly at 3 centimeters. So that decimal point is actually important, and we'll get into why that is in a little bit here. But that decimal point is letting scientists know that, hey, we know for sure that this falls at 3.0 centimeters. If you just saw 3 centimeters, there's a little bit less certainty with that, okay? All right. Significant figures. Okay, so significant figures. It's always hard for me to say, which is why I said it like that. I always mess up when I say it. I always say like some kind of weird version of significant. Anyway, so instead of saying significant figures, because it's hard for me to say, I say sig figs, and lots of scientists do that. It's not just me. Or you'll also see it abbreviated as SFs, or just SFs like that. When I say it out loud, I'll say sig figs. When I write it down, I'll say SF. Anyway, so in any measured number, significant figures are all the digits, including the estimated digit. So what do we mean by digit? Digits are like numbers. So like, 1, 2, 3, 4, etc. Those are digits, right? And then significant figures, what they are is they're used to represent the amount of error that's associated with a measurement. So scientists said, hey, we need to have some way of communicating quickly how sure we are, how certain we are in our measurements. And that's where significant figures come in. Significant figures have some rules. So what I would do if I were you is I would write these rules down. And we'll talk about what they actually mean in a little bit. But these are your sig fig rules. And I would just pop this whole thing into this thing here into your notes. Take a second to do that and then come back. Okay, so let's read these rules. So number 1, all non-zero digits and zeros between digits are significant. All non-zero digits, so anything like, 1, 2, 3, 4, whatever. And then zeros that are between digits. Okay, so if we had like 405, if it's sandwiched between those two other digits, a non-zero digit, that zero is significant. Okay, so let's put significant. It matters. Okay, significant figures are not zeros that act as placeholders before digits. So anything when you see 0.002, 25, these zeros in front are not significant. Let's actually write that down. Not significant. Okay, and then significant figures are zeros at the end of a decimal number. So if you have, let's say 405 again, but then we have a 0 there and maybe a 0 here, which zeros in there would be significant? This 0, because it's sandwiched between those other digits, and then these zeros because they're at the end of a decimal number. If you had, for instance, 4050 without a decimal point, so no decimal point, do you think these zeros would be significant? This one is, right? Because it's sandwiched in between those other digits. But would those end ones be significant? No, they would not. And we'll talk about that in more depth in a minute. Okay. So let's just make a note on these that they are significant. All right, I know this is a lot. It gets more intuitive as you do it more often. Okay, significant zeros and scientific notation continued. So this is just kind of explaining what I talked about up here, but we're going to do it in more depth. So zeros at the end of large standard numbers without a decimal point are not significant. So for instance, these zeros here, because there's no decimal point anywhere in that number, those zeros are not significant. So how many significant figures does this actually have? Well, the only sig fig in here would be this 4 because it's a non-zero digit. So we'd only have one sig fig. And what's kind of nice about scientific notation is that in scientific notation, the number to the left of the multiplication sign, that one is always telling you how many significant figures you have. So you'll notice that here there's only the 4. That's one sig fig. Here there's 8 and 5, 2 digits, 2 sig figs. Okay, so that's why sometimes it can actually be easier to report your numbers in scientific notation. But if you struggle with scientific notation, you can certainly write it out like this. That's okay, unless the question asks you specifically to write it in scientific notation. Just be careful when you write it like this, because you might be tempted to say that there's 1, 2, 3, 4, 5, 6 sig figs, and there's only one because there's no decimal point. Okay, and then zeros at the beginning of a decimal number are used as placeholders and are not significant. So just like I said up here, these zeros are not significant. So these would not be significant and these wouldn't be significant. So how many sig figs do you think this one has and this one? Yeah, this one has 1 and the other one has 2. And if you wanted to, you could look at the numbers here and you'd say there's 2 digits and 1 digit. So that's how many sig figs each of those has. All right, so honestly, I really don't think that me telling you all of this really helps. The best way to learn how to do sig figs is to actually do problems that involve sig figs. And I know it can be really confusing at first. So let's go through some of these. So this learning check, let's do the first one together and then you can do the next 2 on your own. So for A, we have 0.002650 meters. All right, so the first part of the question asks us to identify the significant and non-significant zeros. So the significant zeros, where are those? Yeah, this last 0 is significant because it's a 0 at the end of a decimal number. So if we go back up here, significant figures are zeros at the end of a decimal number. Okay, so that 0 is significant. So let's say significant. What about these zeros over here in the front? Are those ones significant? Sorry, that's those ones. They are not significant, right? Because they are leading zeros or placeholder zeros, not significant. So even though we have that decimal point there, right there, those zeros, because they're in the front before all the digits, they're not significant. Okay, so let's, try B on your own and C on your own, and then come back and we will talk about it. All right, so 43.026 grams. All right, so how many, which zeros are significant in this number? All of them. Yeah, there's only one 0, and it's sandwiched between digits, non-zero digits. So that one is significant. All right, let's try C. We have 1,044,000 liters. All right, so which ones are significant, which ones are not significant? Well, we said sandwich zeros are significant. So this one is significant. I'm going to just say sig because I don't want to say the whole thing. What about these zeros at the end here? These other zeros. I kind of give it away because I put them in blue, but these are not significant. Why aren't they significant? Yeah, there's no decimal point in this number. If there was a decimal point right here, would they be significant? Yeah, they would, because now there's a decimal point. Just like here, these are significant. So zeros at the end of a decimal number. Okay, even if there was a decimal here, right there, those zeros are significant because they're zeros that come at the end of a number that has a decimal in it. So the decimal point really quickly lets us know if we have a significant figures. Just as a side note, before we try to write these in scientific notation, say you had a number 403 with a decimal point and 403 without a decimal point. Oh, sorry, that's a bad example. Let's do 403, 0, and then with a decimal point. There we go. That's what I want. Had a brain freeze for a second there. Okay, so 4030 with a decimal point. This 0 here is significant because of that decimal point. But if we don't have a decimal point, that 0 is not significant. So this number would have, or sorry, this whole number would have 4 sig figs, whereas this number here only has 3. Because now you do count that sandwich 0, but you don't count that end 0. I know it's really weird. Sometimes these sig fig rules can be really annoying, but it is important. Okay, so let's go ahead and try to write these in scientific notation. So this will be a good review for learning how to write in scientific notation. Let's just make like a category here. Okay, so for A, in scientific notation, how are we going to write 0.002650 in scientific notation? The way that I do it again is I move the decimal point 1, 2, 3 times so that it is, I'm creating a number that is between 1 and 10, right? So that's going to give me 2.650 times 10 to the what? -3. Yeah, remember, this is a small number. so we're going to have a negative exponent. If it was a large number, we'd have a positive 1. And then I knew that it was 3 because I moved my decimal place over 3 times, right? 1, 2, and 3. All right. And then you'll notice that we have 4 significant figures here, right? Let's write that down, 4 sig figs. So how many should we have over here? We should have 4, and we do. Because I reported all of those digits after my decimal number. Or at the end of my decimal number, I should say. Okay. All right, for the next one, 43.026. Let's go ahead and make that into scientific notation. We're going to move that decimal point until we have a number between 1 and 10. So that's going to be 4.3026 times what? 10 to the positive 1 or negative 1? Positive 1. Yeah, because this is a bigger number, right? It's not it doesn't have all these zeros in the front. So we know that it is, or it says, you could also think of it as it's a number that's greater than it's at least 1 or higher. It's not like a fractional number like this is. All right. 104400. Oh, 000. Okay. Now for this one, remember that these zeros at the end are not significant. So I have how many sig figs in this number to begin with? I have 4 sig figs, right? Because this 0 is significant. So these 4 digits are significant. Whoops. Okay, so how many should I have? How many sig figs should I have on the left side of my scientific notation? I should have 4. Yeah, we can't lose any. We want to make sure that we keep all the significant figures we have, because that shows other scientists, hey, that's a certain value. Okay, so let's see here. How are we going to do this? So let's pretend there's a decimal point there, just so that we can put this into scientific notation. So we're going to move that decimal 1, 2, 3, 4, 5, 6. I'm moving it left 6. So what is my exponent going to be, positive or negative? Yeah, it's going to be positive. You could think of it as moving left as positive. You could also think of it as big number, positive exponent. Okay, so let's write this out. We have 1.044 times 10 to the positive 6. And the reason I stopped at this spot right here is because none of these are significant. So I don't want to report them. I only want 4 sig figs over here. If I put a 0 there, how many sig figs are in that number? Yeah, 5, because I have a decimal point. I can't lie and say I have 5 sig figs when I don't, right? Okay, I'll get off my soapbox now. These are just checking our answers. I guess we should probably check that my answers are correct. So 2.650 times 10 to the minus 3. Oh my gosh, I forgot my units, you guys. Why didn't anybody tell me? Okay, so the first one we got correct. That's great. The second one, we forgot to say how many sig figs we have. That's actually my bad. 1, 2, 3, 4, 5. Oh, I was counting and I thought I was crazy. There are 5 digits. Okay, so 5 sig figs. Sorry, I don't know why I'm zoomed out so far. And then 5 sig figs here. All right, so that's correct. And then the last one is also correct. Yeah, so great. Still got it. Okay. All right, keep moving on. I know this is getting kind of long. So exact numbers. So exact numbers are things that are numbers that are not measured and do not have a limited number of sig figs. So we don't report sig figs for exact numbers is another way of saying that. And I'm actually going to write that down. We don't report sig figs for exact numbers. And that's because there's no degree of uncertainty. Remember, sig figs are there to show other people how uncertain that measurement is. How uncertain are we in that measurement? How much error is there? If you have numbers that are exact, that are counted, that we know, that we're not measuring, right, with human error, or even a scale can have error because that scale was created by humans. So when it's exact, we don't have to report sig figs. Okay, so numbers that you obtain from counting, if you have 8 cookies in front of you, you're not measuring anything, right? You're just counting. You have 8 cookies, right? You're not saying, I think, you're not taking a measurement. Okay, same thing with like 6 eggs. And then also definitions that compare units. So this would not be a measurement. It's a unit that you use to take measurements, but it's not measuring anything. It's just saying, hey, 1 quart is equal to 4 cups. That's a defined exact number. 1 kilogram is equal to 1,000 grams. If you have a kilogram, you have 1,000 grams. Okay, so that's an exact number. I'm just going to skip that. And then that's going to be in class. Okay, so that's it for today. I hope that made sense. If it didn't, let me know. We can always go over it more, and I have lots of examples to share. So, all right, I'll see you guys later.